Wow, this is good. Thank you for coming. Thank you, Paul. Thank you, Steve. I hope to meet you at some point for organizing this meeting. I think that's an exemplary effort because I believe in engineering. What we need to do is change the world. And the only way to change the world is to talk to the people that actually do it, namely people in industry. And I think that's wonderful that we have a meeting where we actually interact with people in industry. I think it's, we should do it in every area. In 2005, after I had a little bit more time, I did only 3 things rather than 4 things that I typically do. So I decided, okay, what's the next thing? And I thought maybe this flash memory stuff. So I went and talked to a few people in industry, different companies. And I asked them, how does it work? Because I didn't know anything. Specifically asked them, if you take a transistor, a floating gate transistor, and you measure the voltage or the charge on the floating gate, will you know what is stored in the floating gate? And they said, of course. And I told them, in this case, we can do something here. And I said, why are you saying it? I said, because you cannot figure it out if you look at the disk and a disk drive, because there are so many other layers of abstractions, modulations. And I said, what is modulation? So I went back to my office, and I was very happy, but I had no ideas what to do. So I encourage you, as especially the graduate students, I think the other people know that, when you think about something, try to think about what's going on there and whether the paradigm is really the right paradigm. And maybe it is, maybe it isn't, but question everything. I changed the title, Paul. I hope it's okay. I like to start with a puzzle. Do you know what this item is? Anyone? I'll give you a hint. This is non-volatile memory. I'll give you another hint. This is actually a bone of a monkey from 20,000 years ago. It's an early storage device. Notches on bones were the earliest way to record information. Actually, there is an earliest one that I don't have a picture of. It's called the lebombo bone. Has exactly 29 notches on that, and it's from 40,000 years ago. I think it's the best non-volatile memory because it's still with us. And the other reason it's the best is because maybe you know the answer to this question. What does it mean why someone 40,000 years ago will put 29 notches on a bone? Anyone? Sorry? Sorry? Lunar calendar. The lunar cycle. The reason I say it's the best non-volatile memory is that the information is still relevant. Because as you know, most of what we store becomes irrelevant very quickly. This one is still relevant. There are 29 days in a cycle. When you live 40,000 years ago, there are not too many natural numbers that you can reason about. People didn't think about the concept of a number. 29 is one number. Another number is 12. And then there are not too many other numbers, maybe the number of year in a year, but those 29 and 12 are the most natural numbers at that time. You don't want to count the sky, the stars in the sky or your ship, because then you fall asleep. So the lunar. Do you know who this guy is? I'll give you a hint. He is not from 40,000 years ago. he was a high school teacher. He was teaching science. And he invented in 1932 the electronic test scoring machine, before there were computers, digital computers, because he was a great engineer. And in fact, IBM bought his little startup. His name is Reynold Johnson. And I don't know how much money they make out of the test scoring machine, but in 1952, IBM asked Mr. Johnson to go to San Jose. It's a city all the way far in the West Coast, and to start a group there and try to build a disk drive based on magnetic recording. And he did that. And in fact, it happened in 1956. So it's exactly something like 55 years ago that we had our first disk drive. That's also led to the development of IBM Almaden, which is, of course, up on the hill. And that's where for the first time I met Paul. IBM became the leader in producing disk drives, and especially in all the signal processing and coding for disk drives. And actually, Paul Siegel was the manager of this group. And as a graduate student, I was fortunate to work in his group. And it wasn't related to my PhD thesis. It was a hobby, but it became a great hobby. And you see there, that's a wing C where Paul's group was. And then I ended up working on wing B, where computer science is, and the next keynote speaker, C. Mohan, I think he's probably still in wing B. Are you here? Is it still wing B? Yeah, okay. At that time, there were also cows there. And we used to organize workshops once a year or once every 2 years on coding. This is a system that Mr. Johnson and his team created. Of course, IBM is really good with names, so they called it RAMAC, not iStorage or some other name, but RAMAC. It was 1 ton. It had 50 double-sided aluminum disks, each 24 inches in size. Kind of hard to use it as an iPod, right? It's hard to put it somewhere. And overall, it had an impressive storage capacity of 5 megabytes. That's pretty good for the first one. And that shows you the amazing progress since then. We started with 24 inches that each could store 100 kilobytes. And now I even don't know what the number is. The industry people know better. But a couple of inches and a terabyte. Is it a good, yeah, I'm looking at the person from Toshiba. Amazing. Okay, now I'll show you 2 systems. One is the first disk drive ever built, 5 meg. The other one is a storage system, can be EMC, IBM, Network Appliance, HP. There are different companies that do that. It's a big box. It can store, say, 100, 200 terabytes. Does anyone know how those 2 systems, what do they have in common? What do they have in common? I cannot hear you. They have rotating disk. You get partial credit for that. Any other idea? Wonderful. Think simple in life. What's your name? Paul. Nice to meet you, Paul. They're both 1 ton. What does it mean? It means that, again, we got to a point where we are doing something that needs to be improved. That's what it means. We are back to the beginning. If we need to put many 1 ton systems that consume more energy for cooling and power in their lifetime, than the cost of the product itself, then something is wrong. Imagine you buy a car, and when you buy a car, you say, okay, you pay $30,000 for the car. However, you are going to spend in the next 5 years $100,000 for gas, oil, and other maintenance issues. You'll say, this is stupid, I'm taking the bus. So we need to take the bus. Okay, that's the point we are, and that's why we have this workshop. The other thing is we have more data, because we got so good in building those things that, and then everyone has a Facebook account. Everywhere you go, people take pictures, and we just have more data. So having an environment where we have 2 to the 18 bytes is not something that is imaginary. It sounds imaginary, but it's not. And if every disk is just 1 tera, then it means that in one place we have 1 million rotating disks. I get a headache just thinking about that, honestly. And that's a big headache. So there is an issue with reliability, with performance, with power and cooling. In fact, many of the systems that companies sell today, the reason that they have so much capacity is not because of the need for capacity, it's because of the need for performance. This is like selling Mercedes, and you don't know how to build one. So what do? You take 1 million bicycles, you put it inside the Mercedes, and then you sell it. And then it moves okay, but it's very expensive. So that's what we do these days with the disks. So what we want is some solution that we will have random access. I'll talk more about random access. High throughput, low power, non-volatile. Wonderful. And many more, by the way. This is just the beginning. Of course, our imagination will take us to new places. And there are different technologies, flash, PCM, graphene. And the most important one are the 3 question marks, because actually in this workshop alone, there are like 3 other technologies. And actually we don't know, so it's a lot of fun. There is an interesting asymmetry in all of those, or maybe most of those devices or technologies. It's very easy to read. Very easy to read. We just measure something. Can be resistance, can be capacity, can be charge, I don't know. We measure it. It is relatively more difficult to write. And then there is a new notion, a notion of erasing. That's really painful. You know, when you think about disk drives, there was no notion of erasing. You just write over it. And with those new technologies, we still didn't figure it out. We have the notion of erasing. By the way, I don't have a notion of erasing in my brain. I don't know how it works for you, at least not one that I can control. It's kind of getting erased on its own all the time. So there is a very strong asymmetry, and we need to think how do we deal with it, and whether really that's what we want. That's a big issue. We need to think maybe about devices where we don't have this asymmetry. The other thing is that erasing is a destructive process. I always wonder how come there is no erasing process in our brains. Well, maybe because it will do something bad to us. But in multi-level flash devices, there are different numbers, you know, but in any case, this number is small. Because if you want to use it for your camera or your iPod or any other device, then 10,000 is a good number. Why? Because there are only about 300 days in a year. 10,000 divided by 300 is a big number. And are you going to erase everything on your camera once a day? Probably not. So it's a good number. However, if you want to put it in the enterprise, because that's our dream, then it's a big problem because the applications don't know about going to sleep. And they work all the time, and they write a lot, they erase and so on, move data and so on. So it's a big problem. As a result, and because of other reasons, the way we write is typically different than the way we erase. So we write in some chunks, maybe pages, maybe single cells, who knows. Then we erase in bigger blocks. Why? Because it's painful, because the logic is different and more complicated. So a different reason. It's again because we have those three different ways of doing things that also it affects the architecture. So we can increase cell by cell, but then if we make a mistake, say in writing, or say we have an error, then we have a big problem. It's like the etch and sketch game that my kids had. I didn't have that. And it was very frustrating for me because they asked me, can you do something? And I said, I'll try. And I always failed. Why? Because I'm really bad in sketching. And here, if you make one mistake, then you need to erase everything. After twice like that, the kid will take the etch and sketch and go somewhere else. Find someone more competent. And I think that's a problem. So I'll tell you a simple, okay, writing. So etch and sketch. The way I think about writing is, and the etch and sketch is that it's like parking a large semi-trailer or a large truck. You come in and you are driving fast on the freeway, but then when you get to the parking lot, you're very careful. You don't want to hit the other cars around you. You don't want to hit the wall. So you become very slow. And that's the way we write in Flash, is that we have to do it slowly, iteratively. So I like this game of golf that I invented for the sake of illustration. So we have two yellow lines. We have a blue ball. We have a red arrow. And the red arrow can hit the blue ball. And the goal is to put the blue ball between the yellow line. So we are very careful because we don't want it to go above the yellow lines. So we are very careful, and then we do it again. And, well, this didn't work out. So that's really bad. So as a result, we are a bit more careful now. It worked out. And in fact, if you look at current Flash technology, we have, if we wrote to get to a fixed level, say represented by 0, 1, 0, then we need to do it slowly because we don't want to overshoot. And in fact, typically it takes something like 5 iterations, maybe more, maybe less. But you can see that it's a problem. It's slow. And also imagine that someone comes to you and tries to explain to you something and does it for 5 to 8 times. Typically you get a headache from that. So that's bad for the physics also. So we destroy the physics by going through those iterations. So here is a simple idea we had. You know, for the student especially, if you didn't know that, all of us that do research for many years never had a complicated idea. We always had very simple ideas. Then we looked at the simple idea and we had another simple idea. And then we looked at the 2 simple ideas and we had another simple idea. And then at the end, there is a picture with many simple ideas that together looks like, how did you get there? But it always starts with simple ideas. So don't look for the big combination of simple ideas, just one simple idea. So the simple idea we had is that instead of representing things with absolute value, let's represent them with relative values. So we are going to be wasteful in a sense. So we will represent a 1 if one cell is bigger than the other one, and a 0 if it's the other way around. Now there is no problem of overshooting, because if I want to update it, I just push it high. And what can happen? I didn't make it bigger, so I'll try again, but at least I don't need to be too careful. So this was the idea. And then you say, okay, well, the second simple idea is Y2. Maybe I can represent it using permutations, because this was a permutation on 2 elements. So if you look at the permutations, and below you see the value 4, 1, 2, and 3, which are the kind of the values, if you think about real values of the cells. But in fact, there is another way to represent a permutation, and basically you start from the top and you say, what is the index of the highest one? So it's 1. What is the index of the second one? It's 4. What's the index of the third one? It's 3, and the last one is 2. So that's another way of representing an information permutation, 1, 4, 3, 2. And then the operations that we want to do on permutation is something where we don't worry about overshooting. So we want to take an element and push it to the top. For example, we can take 3 and push it to the top. And now when I look at the kind of vertical representation, then I get a new permutation, which is 3, 1, 4, and 2. Wonderful. So what do we do with it? What do we do with it? So basically, the idea is we have physical cells originally, but instead we took physical cells and we decided to represent it as a logical cell, a bunch of cells that each of them represent a permutation. And instead of working with absolute values, we work with relative values. Okay, so what are we going to do with it? So the next idea was, let's take this logical cell, and instead of saying I'm going to represent a single string of bits into each one of those logical cells, what I want to do is implement a counter. The counter has 2 operations, is increment, so it goes to the next value, or erase, and I zero it down. Why do I do it? Because it's very natural with property of Flash where everything goes up. So I do want to go through values in increasing order. And if you think about the real cell, then we also keep pushing it up. In a sense, it's also a counter that we keep increasing it. It's just we decided that every value in the counter corresponds to some bits. But I just want to think about counters. So then the next simple question, I'm telling you how we did this research. The next simple question is, how can we implement counters with permutations? So what it boils down to is, can we go through the whole space of permutations by doing every time only a single push to the top operation and come back? And this way we can have a counter. So what do? We go to the whiteboard, we have a question, and we don't know what the answer is. So we write the first permutation, 1, 2, 3. And because we need to see if it's even possible. You know, we have about 1,000 ideas about stuff, and maybe a couple of them work. But we need to check each one of them, because how do we know if it works or not? So we start with 1, 2, 3. From 1 to 3, I either push 2 to the top or I push 3 to the top. So I either get 3, 1, 2 or 2, 1, 3. And then you can keep doing it and get the graph that relates to the push to the top operations on permutation. And the question in this graph is there a cycle in the graph that goes through all the nodes? That's the question regarding to our ability to implement a counter. So it is on the whiteboard, and we try to find a cycle. Do you see any cycle? That's what we did. We just look and we say, oh, okay, there is a cycle. Here is a cycle. Then myself and collaborators, we keep looking. Oh, there is another cycle. Okay, you have 1, 2. Oh, there is another one. Okay, there are cycles. That's wonderful. So it's true for n equals 3. Then we say, what about general n? Just to show you how it works. So that's just going through the cycle and how it looks on the actual values. And then for a general construction, the first idea we had is something recursive. We just keep, say, 4 in one place, go through the cycle on 3, And then we have 2, 1, and 3 at the top. We bring 4 up. And now we have 4, 2, and 1 at the top. So we can actually run the same cycle on 3 on the top 3. What's the problem with this approach is that we have a huge jump for the 4 in this case of n-1 factorial because everything is flying away from it. And I'll talk more about it, why I don't like it. So we ask ourselves, can we do it such that the values fly next to each other and still we get a cycle? And the answer is yes for arbitrary n. And I will just show you an animation of a cycle of length 24. This is for the case of 4 cells that goes through all the values and has the best jump possible, which is they're basically always all together. So that's wonderful. And we know how to decode from that and code different ideas. Why do I like them to stay together? Why do I like them to stay together? Because we had an idea which is, again, it's one of those ideas that in a few years people will say, this is completely stupid. And I feel that right now I cannot substantiate it, but that's one reason we did it, is that perhaps when we write, and you can say, hey, what are you doing? There is a ceiling there. You keep going up. You didn't hear about 8 levels, 4 levels, 16 levels. Well, I'm thinking about deflating it slowly. So think about us. We go to sleep. We have a headache. We heard enough talks. We are in the workshop. This guy with an accent talked for an hour. So you go take a nap. You wake up from the nap. You are ready to get more information. So what I think about is that we have a mechanism that slowly deflates it or leaks it out. I think in some technologies is more reasonable than others. For example, things that relate to temperature, like PCM. You might say, okay, maybe I would just bring it down slowly and make sure I don't lose it. And in a sense, you never need to erase. I don't like this erase operation. I want to make sure it happens all the time, and I just keep writing on top of what I have. So that's kind of a strange dream that I have, and maybe it's not useful at all, but maybe it is, depending on the technology. I'd like to give some credit to my co-authors. Andrew was my grad student, but that's something he didn't do. Andrew, are you here? I don't know. He didn't do it through his PhD thesis. It's something that we started working on after he was a professor already. And this project, all of it, wouldn't be the same without Andrew. He really was a key person in the project. I just happened to know him. And I just happened to be the one giving the talk, but he could have given the talk as well. Robert was a postdoc in the lab and is moving to Hitachi soon. Hitachi was in previous life IBM Almaden storage and so on. So there is a cycle there. And Moshe was a postdoc in my group and is now a professor in Ben-Gurion University. There is some early work on the topic of representing things with permutation. Whenever you do work in things related to coding and information, take a look what Jack Wolf did. Because it's very likely already did something, had this idea one way or the other. I'm not joking, and not because he's here, but it was true in my case, You look at LDPC, suddenly you discover, hey, this guy played with those matrices, linear codes a while back. So I'm serious about it. So I'm very grateful you came to the talk, Jack. And then there is a lot of recent work, some of it by my students, some by other people. And there are many versions of that, bounded, partial, local. The one I'm most excited about these days are the compressed rank modulation. So we somehow know how to go between permutation without going too high. And we found a way to go to the next permutation without having the problem of the overshoot, but still we don't need to push it all the way to the top. And it opened up a whole avenue for research. That's the work of Andrew Jiang and Eyal. And Eyal, are you here? Somewhere. Yeah, hi. And I think there are many other work. Bella Bose is here, and I don't think Sasha Barg is here. But I think at this point, I'm very happy to report that I don't understand most of the most recent work on the topic. I barely understand what I'm doing now, so it took off. So we showed how to do a collection of counters. And the question is, what do you do with it? So we want to have a storage system that stores bits into a collection of counters. Why? Because we know how to do it. And here is the idea. We want to write a stream of bits into a collection of counters. And the most important idea is we don't want to write arrays. I don't like this arrays. If you want to remember one thing from my talk, I don't like the arrays. I want to rewrite, maybe arrays every now and then, but I want to be asleep when that happens. So what do I mean by that? Suppose I want to write a single bit into, say, 4 counters. So if the bit is 1, then I increment the counter. If the bit is 0, I also increment the counter. I basically represent the bit as a parity of the value of the counters. And that's it. If it's even, the value of those 4 counters, you can sum them up. You can also fill them up horizontally. Then suddenly it works. So you can write forever. What do you lose? You don't use the whole capacity. The notion of capacity for storage is wrong. Why? Because I don't use my whole capacity as a person. I even don't know what it is. Storage systems don't use their whole capacity. Capacity was invented to charge you money. And I think over time it will lose its meaning. I'll show you later why. There is an exponential gap between how much you can write, how many bit changes you can write if you don't worry about always writing the whole capacity versus writing the whole capacity. So you can do much more. Much more. I'll show you another example. Say we have 2 counters. So one approach, this is 2 bits. I don't know the language. So 4 levels. If you use what people do today, you can write 2 bits per counter because every value has correspond to 2 bits. So overall, you can write 4 bits. However, if you look at how many bit changes you can record, and say you do the simple thing, which is assign 1 bit per cell, then you can 3 changes per cell. So overall 6 bits instead of 4 bits, just on this simple example. And the question we ask ourselves is, can we do better than that? Can we do better than 6 cells? Because you see the red one, if we had 3 changes in these bits, we are done. We need to erase the whole thing. So we need to think maybe there is a way to do better. And the idea is to combine and do it together. And I'll show you the idea. So we start with a value 0, 0. This is a value of the cells. No rank modulation here. Think about counters. So the next one, it can go from 0, 0, which is in the block, in the square, is a value in the bits. It can go to either 1, 0 or 0, 1, because only one change is allowed. Okay? So we put 1, 0 in the counter for 1, 0 and 0, 1 for 0, 1. And then from 0, 1 and 1, 0, it can go either to 0, 0 with one change or to 1, 1. So we assign 1, 1 to 1, 1. We assign 2, 0 to 0, 0. And now we are happy because we can go to the 1, 1. However, we cannot go from 0, 1 to 2, 0. Why? Because we cannot get there by incrementing the counters. So we need to add another one. And you get the idea. We get a graph that is legal in the sense that we always go up by incrementing counter. And this is, in fact, can be repeated. So this building block, so you can actually store information 2 bits into 2 counters in an optimal way. In what sense? That you cannot do better than that in terms of how much you store in the worst case, how many bit changes per bit. And we have right now an optimal general construction to write k bits into n counters. And again, there was a lot of work on the topic. I think the early work was with a paper by Rivest and Shamir, which is a bit different. It's related, it's a bit different, because they actually wanted to use, in a sense, in the first write, the whole capacity. And as I told you before, look for the papers of Jack Wolf when you try to find a good topic for your thesis. Because, of course, also Jack worked on that in '84. And then Paul and Eitan and their collaborators worked on that here, had some nice result. I think the kind of the current state is the last paper that we submitted to IEEE Transaction on Information Theory with Andrew and Mike Langberg and Moshe, called Trajectory Codes for Flash Memories. And I think we address many of the different trade-offs there. Also, the work of a group from Harvard of Mitzenmacher, they address a very interesting question, which is, I don't care about worst case, let's look at average case. You know, on average, how many bits and so on. And they did a very nice work there. So there are many different activities related, again, to this topic. But I want to bring it back and say, what is the architecture that I'm proposing? Is to write a stream of bits into logical cells. The logical cells are counter, and we use rewriting codes for that. And hopefully, if we implement the counters well, we never need to erase them. They somehow always get erased as a background process. And one approach is to implement the counters using rank modulation, but you can do it in any other way. So the rewriting codes is, in a sense, independent idea than the rank modulation. Who heard about graphene? Okay, some people. That's what I did in elementary school. I played with graphene because we had pencils and I was bored, so I put it all over the table. My brother, I was in Israel a few weeks ago, and my brother found I had something that doesn't exist today, a wooden box where you keep all your pencils. You remember, it opens this way. I basically cried when he gave it to me. Of course, it had graphene all over it because I was bored, so I did different things. It was messy. And he said, so what did you do with it? I said, I don't know. It looks messy. He said, don't clean it up. That's the whole idea. So graphene. I want to tell you some work I did on graphene beyond elementary school. So I want to remind you something about punch cards. Who knows what punch cards are? Okay, that's good. Punch cards were invented for textile about 210 years ago. And then 100 years after it was invented for textile, Hermann Hollerith used it in order to do the recording of the US census in 1890. And of course, created a company, and this company was part of IBM. Everything was IBM, you know, Reynold Johnson, IBM, Paul Siegel, IBM, Hermann Hollerith, IBM. Jack, did you work for IBM? No. I told you to look at Jack's papers. No IBM for Jack. For those 50 years between 1900 and 1950, they were the primary medium for storage, control, and everything. So overall, 150 years of punch cards. And then in the 50s, we got the tapes and the disk drives. The punch cards still continued, but we don't use them very often unless we vote. Right? Voting is, I worked on the voting project, so I discovered the punch card technology. Nano punch cards, okay, graphene. So graphene is just one piece of carbon that is only one atom in height. And is it last year or 2 years ago that the people that discovered it got a Nobel Prize? Is it? I don't remember. But has amazing properties, amazing. And one of the amazing properties is that if you apply voltage, then at a certain level, then this voltage breaks the bonds, and you get a crack. A crack, and you can see it also, if you have the right technology for looking at it. And the amazing thing is that if you apply voltage at a lower level for a longer time, the bonds get connected again. So this is a dream. Like you have a piece of paper, you can tear it, and then you look at it, you say, boom, and then it gets connected. That's graphene for you. Wonderful. When it's broken, the resistance is high. When it's connected, resistance is low. It's conducting. And Mark Buckhart, that is applied physicist, worked on that, and he did some very nice work. And he was looking for like 2 levels. I told him, don't worry about 2 levels. We'll do rank modulation. And I explained it to him. So we actually built these circuits that you see here, where we put 2. And we did what we did, which is change the voltage and keep rewriting. And you see that the green and the blue at the lower graph, that they are different from each other. The other striking phenomena is that if you look at the 2 values of the graphene, then over 24 hours, they're changing. It's noisy, it's room temperature, but because it's relative, they fly one above the other. So that's pretty amazing. Graphene has issues. It's too slow, the switching, and so on. We have now a project where we try to control resistance in a graphene without breaking the bonds, just by stretching it. You can put it on a 2D configuration where you stretch certain points by applying voltage, and then as a result you change the resistance at this point. And that happens much faster because you don't break any bond. You just change the distance between the atoms. This sounds like science fiction, right? How do I store information? I take 2 atoms and make them a bit farther apart. Wow. So that's another dream. I don't know what will happen with that, but I'm very excited at this point. Okay. I'm pretty good. I want to tell you about something beyond devices and coding and signal processing, just to kind of increase your appetite for the break. So we talked about benefits, random access, high throughput, low power, non-volatile. I think the random access is the key for key enabling change for the future. Why? Because it will be the first time that we will have the ability to randomly access information in the enterprise at large quantities in a way which is not sequential. Because disk drives are sequential. No matter what you do, you write streams of data and it becomes sequential. And there is a lot of money invested in caches and stuff like that to make it look as if it's not. But I think the random access is a huge advantage. And specifically, what it does, it enables content-based memory, right? When you know what content-based memory. If you don't, I'll show you an example. Say two brains meet each other. And the first brain tells the other brains, I have tomatoes in my backyard. So the brain that is having tomatoes in his backyard doesn't need to pull a tomato from his pocket and give it to the guy, the other brain. Why? Because when he tells him tomato, he knows what tomatoes are. There is some common language. There is a dictionary that we can communicate and store information. So now suddenly I tell the other guy, I have tomatoes in my backyard. Boom, he put it in his backyard for Shuki, and he said there is tomatoes there. But he doesn't need to store the whole notion of tomato again. Why? Because it's stored already. It relates to salad, it relates to being messy, it relates to ketchup, it relates to many things. And I think the future in storage is to organize things this way. And it's possible to do it with random access, impossible to do it with sequential. So I'll show you another illustration. Here is a brain running around. We have a storage system with 10 cells. 10 cells. And now there is a tomato coming in. Tomato is big. Maybe 4K, maybe 4 meg, I don't know. A block, tomato. Brain looks at the tomato, said, I need to store it in 4. Said, did I see a tomato before? No, because it's empty. My head is empty. So what do? I put the tomato in my backyard. I put a little tomato in 4. Now I know that I saw the tomato. Now comes another tomato. Need to put it in location 8. This is just the same interface as normal storage system. Okay. Brain looks at it, says, I've seen a tomato before, so I don't need to store it. I just need to remember it's in 8. So, okay, I'll put a little one in 8. That's it. No storing. Okay, now comes a banana. Didn't see the banana before. Want to do it in 2, so I do the same thing, and then so on. So I have a whole backyard full with stuff. Now, given this organization, you can do amazing stuff. I'm not going to go through all of those, but I'll show you the simplest operation, which is someone tells you, can you copy location 0 to 3 to location 5 to 8? The brain looks at it and laughs, because copy is no work for him, because it just moves it here. No need to move any data. That's it. That's content-based or associative. There are different words for that. To do it with sequential is going to break the spindles. Doesn't work. With random access, it's going to happen. In fact, it's the first time I talk about it in public, about this idea, because I got clearance for that. Remember the word clearance for? You gave me clearance many times. I'm involved in a startup that's what we do. We build an enterprise storage system that's all based on content. and it's using Flash. And the good thing is that it works. You know, good ideas are good, and even better ideas sometimes work. This one works, and it works very well. So I want to just conclude by talking about the amazing opportunities of the future. Amazing. And I think, again, thank you to Paul and Steve for starting these meetings. I think that's where the future is. I think storage is more important than communications. We will be managing storage, whether it's here or maybe the storage moves from here to San Francisco. So storage will be a leading challenge in the next coming years. I think the first level are devices, and it's not clear what is the future technology for NVM. We'll see many iterations on that. But some good things will emerge, and it will continue. I think the next one is the whole notion of the memory architecture and algorithms, signal processing and coding, and that's some of the ideas I showed earlier in my talk related to different modulation schemes, error correcting codes, and so on. And of course, all of those layers are connected. I think the third one is what do we do is it at the system level? Can you build a scalable random access? Sounds simple, right? But say I give you a box that can store 100 tera or 50 tera. And I give you another box that stores 50 tera. Can you put them together such that now you have the sum of the two? And can you put hundreds of them together? So trying to build scalable random access which is content-based. That's a big challenge. I think probably Mohan will talk about it. He's an expert in databases, and he knows much more than I do about it. But I think what will happen is the API to storage will change. API is an interface to the storage. Right now we have read, write, I don't like to say arrays, snapshot, copy, different services. I think, and we have this strange notion of file. I think the notion of file will hopefully disappear at some point. How will the databases of the future will look like with new storage? Can storage give us more functionality? For example, can we do a search on data in the storage device itself? I think what will happen with the new type of storage devices and architectures we build is computing and storage will get closer to each other. Because right now, it was very nice for us to say, hey, this is a storage company. They build boxes to store stuff. I'm a database company. I build databases. I'm a computing company. I do computing. But I think we will see more closer integration between computation and storage at the lower granularity. We will have a different interface that we can ask the storage for questions. So I think that's basically it. And thank you very much. And I'll be happy to take questions. Yes, please. Can you say your name?
For the content-based work, what is the role that index? It seems like it is related to search. In order to recognize that you have seen a tomato before,
yes,
you need to be able to.
It is, of course, related to search. Yeah.
So, do you use indexes?
Well, you get 5 gig. How do you know if you've seen it before? One option is to look for everything. The other one is to use other techniques like hashing, data structures, and so on.
So that's what you're doing.
Probably. I need to call to get clearance. Any other questions? Yes, please. Thank you for being brave. You know, when I was a student and I was sitting in the audience and they said questions, I had so many questions, but also I was very fearful because I was afraid to maybe ask a stupid question. There is no stupid questions.
Did I hear you say that for one of your mechanisms you try to get the counters even?
The counter didn't.
I might have misunderstood this. Do you try to get counters to be at to get the cells at even level?
Yeah, I'm trying to build a counter using permutations such that the levels in the permutations are close to each other. So the state is defined by the permutation, and I don't want to get the levels too far from each other. Why? Because there are different issues. One is it takes longer to catch up, but the other issue is that I have this idea that one day it will just melt down slowly.
Right, so my question was, does that make the problem of overshooting back into the picture?
No. We still, in this case, we update. That was a key challenge. We were not sure if it's possible. We still update to the next state by pushing one of the elements that is not at the top to the top. We still use the same operation, yeah.
It's still relative.
Yes, everything is relative, everything is pushed to the top, but it's staying together.
So if you do overshoot, you can push it further.
No, you never overshoot. Your goal is to be the tallest one, and that's it.
Okay.
Yes, please. That's an excellent question. So with what I described as deflation, you can, the question was is that you can lose the things that are low. You can also lose everything. So we need a mechanism to sustain it, which I didn't discuss. Yes, please. Another interesting and very deep question. We did some analysis on that, and we believe that there is about a factor of 2 in the number of levels that you effectively use. But we are dying to work with someone that will actually try it, because right now when we work with fixed levels, then we have to be more conservative, and it keeps them apart enough such that we don't make mistakes. But if all what we need to do is just decide if something is bigger than something else, de facto you can get more levels. Yes, please. You have to stand up because I will not see your face, and then I will not understand.
You mentioned that the notion of files will disappear in the future. There has been a lot of work earlier on the object-based storage, which is
Right.
representation of content, but they haven't been commercially successful a lot, though it's been long. Do you see any reason why?
Yeah, I think I know about this work, and so the question is related to object-based ways to reason about storage, and I think that supporting it using the current storage system is just hopeless. And I think if you think about something that looks like an infinite memory to you from an application perspective, that can be give you very high performance, and perhaps those approaches will work. So in a sense, you want to start a program and not start reading from a file. You just start it and all the data that you need is already there. At least seems like it's there. And I think those things are possible with changing the way we interact between computation and storage. So I strongly believe it will change. It cannot change for everything. There's still Fortran code, running. And it takes time. The question is what will happen in the future. And okay, I will let other people ask questions. Any more questions? Yes, please.
For modulation, like the number of bits you can store is log to the base 2 of n factorial versus if you had like q levels, you could store q to the power n, which is much higher than log to the base 2.
Right. So the question is, you lose in terms of capacity, because when you have, say, n levels on n cells, then you can store log n per cells times n cells, it's n log n, right? That's what you were saying. And what you can store with rank modulation, if you use everything, like which I don't think about it this way, but suppose you use everything, you can store log of n factorial. In fact, this log of n factorial is similar to n log n. So asymptotically, it's very similar. Yeah, I think if you talk at 2 levels, or 3 levels, or 4 levels, maybe it's not interesting. But at the same time, the reason we have 4 levels is because we need to make sure that we have big gaps. Yes, please. Yeah, so the question is that there is leakage, and leakage is proportional to the absolute value, right? That's what you were saying. So given that, we need to make sure that if we go, the higher we go, the bigger the gaps are. Which I think it's in this current technology, we need to take care of that. I agree. As long as it's consistent, then it's fine. I think one of the problems with flash is that some cells behave one way and some cells behave another way on the same flash device. Back to 2005, I went to talk to the industry. They described with me all the problems, including those problems and other problems, and I told them I actually don't know how it works. So I backed up everything on my camera quickly. But somehow it works, It's kind of scary how many issues we have. Yes, please. Mm-hmm. So that's some of the things that people do today also. So you can design it in a way that things will be exhausted. So we are working with a bunch of counters. We try to keep them more or less at the same height. So we don't exhaust anyone too quickly. That's a rewriting codes. But maybe a bunch of counters get saturated, and then we logically point to another place for this type of information, and then in the background erase it. So I think all of those things are ideas that are very useful, and some of them are actually being implemented today. Not with the counters, but with actual pages. There are different so-called wear leveling, many other ideas related. Yes, please.
Can you tell us more about the startup?
So the idea is to build an enterprise storage system that is scalable, so it basically can support very large system. It's block-based, for those of you that know that there are file and block. And it's all based on Flash, and it's from the outside it looks like a block-based storage system. Are you recording me with a video? Yes. Okay. And I noticed that when I started the talk. It's fine. I embarrassed myself enough in my lifetime. I think that's more or less the framework, and it's about a year and a half old. And I think this year we will be more open when we show customers that are using it. Yes, please. Yes, so the question is, how do you resolve the permutation out of a bunch of cells? You need to compare each cell to another cell. So part of the project, we worked with a group of Paul Hassler in Georgia Tech. In fact, they came up with some circuit for that. I didn't show it today. And as they came up with a circuit and the architecture, we realized that perhaps a better way will be not to resolve the permutation as a whole, to look at all the cells, but to look at maybe half of them, because this will save time, and it's not going to affect capacity. And that's the work of Jiying that is sitting next to you. It's called partial. I think partial. It's partial. Partial rank modulation. So because the way they implemented the hardware is that they can quickly find what is the largest value out of a subset that they choose. Then they can eliminate one and do it the same. So you actually don't compare, you just quickly find the largest one, eliminate, keep doing that. That's a sequential process. So then we thought maybe we should look at less of only at the top, maybe half of them. So there are interesting trade-offs there. It's a very good question. It's not a simple thing to do. Yes, please. So I think there is a lot of work on. So the question was about durability. So I can take it in many different directions. But Paul and I think Steve studied many issues related to durability and errors that are introduced. We didn't compare this type of behavior if we use rank modulation. And there is a simple reason for that. the flash companies don't have interest to let you touch the analog values in the flash. If you do that, you need to meet many lawyers. If they will do it with you, you will meet many lawyers and you will spend a lot of money. Then they will let you do it. And then you will not talk to anyone if they let you do it. So there are few companies that are actually able to change the analog values in the cell, and they get tremendous advantages as a result. The current way of storing information in flash is wrong. And there is a way to improve it without changing the flash. However, there is an interface that is a trade secret. And I don't have access to it. I don't plan to have access to it because I don't want to talk to 50 lawyers. So there is a whole issue there. But this is a transition. It's a transition. Very soon there will be new technologies. It will be open. And I think at the end, the flash devices should have a standard interface where you can set up the values and not just say write bit here or there. So also the error, like Bella worked on that, we worked on that in my group. The errors are very specific. They are limited magnitude. I think you are giving a talk, Bella. Limited magnitude, because it cannot be that it suddenly jumps very high like the previous question. But still, if you look at SSDs, they use normal BCH codes. So they assume just random errors. Why do they do it? Because they cannot do anything else, because they have no access to the actual values. So that's a problem. Yes. I like memory that I don't need to think about arrays at any point. Which means it's not non-volatile. No, it is non-volatile. Well, disk is non-volatile. You don't make a special event out of erasing it. So it doesn't need to have this overemphasis on arrays. We have special circuits and so on. I think that's a big problem. It's obviously true for what we developed it for, because we had it in cameras and or as a USB stick, and you want to erase it and put new stuff on it. Okay, but if you use it as operating memory, like say my laptop has an SSD, I don't have in mind that I need to erase it. I just keep writing and moving things around. Yeah. If you have any other questions or comments, if you want to talk to me, you want to visit Caltech and talk to me, just send me email. I'm pretty responsive. Thank you.